Okay, so so yesterday we started the magic trick. So the magic trick, in fact, there will be two magic tricks. The first magic trick is what we will do with the existence of two pairs of dual bases for the bilinear form induced by tau. And there will be another magic trick to prove what is called the second orthogonality relation. But before that, let me come back a little bit where I recall all the notation. Okay, so it's good to recall this notation because they will be used often. So you have the hypergroup H basis B. The element of the basis B are xi. Okay. The character of the H are mu I, so they are in the dual. When I say character, I mean algebra morphism. Okay. So to a character that it associates a primitive central idempotent. Here it's written Fi. And so you have this relation, ui fj equal delta ij. That's okay. And you have the similar thing when you consider x star and x double star. So if we identify x double star with h, and we can do that because it's finite dimensional, then fi xi can be seen as element here. But in fact, so what do we have? If you consider the map in x star evaluating at the coefficient of xi, is denoted like that, evaluating the coefficient. It's denoted also like that here. Okay, so it's different from this one. This one is not an algebra morphism. This one is an algebra morphism. But we have, in fact, by definition of that, it's just the coefficient of xi. So if I is different from j, it's 0, otherwise it's 1. Okay. Then you consider the map from x star to the field. So an element is a double dual evaluating at xi. It's denoted like that. And this is an algebra morphism, which is, and this is not this one, which is just a linear map. Okay. And in fact, this corresponds to, you can, but under this identification, xi is an algebra morphism in x star, given by the evaluation at xi. Okay. And the primitive central idempotent in x star is denoted like that. So it corresponds to that. And we have, corresponding to this algebra morphism, and we have this relation exactly as we have this relation. And okay, and in fact, so if you make the proper identification, In fact, this relation is nothing but this relation. If you consider that as a map, it's just in fact the dual of this relation. There is nothing new. Okay. So that's okay. So my suggestion about notation, even if I will need to talk with my co-author, it's not clear we will follow this. But at least what you can see is that the notation xi cover that, and that. Okay. In fact, we could use xi hat instead of xi not, and it will cover that. Mu I cover. So you have mu I hat, which is exactly fi, and so mu I is fi hat, fi not, etc. So we have only four. We only need four notation, and this four notation cover everything. Okay. Under this identification, my suggestion also is to use h hat instead of h star. So we can. This is a suggestion also. To use this notation instead of this notation. So the dual coefficient nijk hat instead of pkij, something like that. I don't remember, in fact. In the dual hypergroup. Then, note that this. So you have this. You have this trivial relation. Where is it? Here. This is 0 or 1. So if you consider the element which is the primitive central idempotent corresponding to this algebra morphism, you have this kind of trivial relation. Idem for that. Idem for that. But now idem for that. What happens if you evaluate an element? If you evaluate this one by this one, if you do that, then you don't have a trivial relation. What you have, you can call that the Fourier coefficient, because you can consider a map from one to the other, a kind of Fourier transform. And this is the Fourier coefficient, but in our understanding, you can just call that the entry of the character table. When you have the character table of a group, in fact, this is exactly the entry of the character table. So here you have something non-trivial, and you can ask also, in fact, what about evaluating that with that? And so what about that, which can be written like that? What is the is coefficient of fg? And in fact, we already know that if you take I equal 1, this is tau, and this is, in fact, the inverse of the formal category. So for I equal 1, here you have the formal, you get the formal category inverse. So what about if you don't take I equal 1? Maybe you have something, some dual Fourier coefficient, I don't know. But there should be something like that. Anyway. So, very good, at least, even if the paper will not, I don't know if we will replace all the coefficient by that, all the notation by that, but at least it's good to come back to this page to this slide to understand what we are talking about, which notation. Sometimes it's more convenient to use this notation or this notation. You use this notation when you are talking about the primitive central idempotent, or you use this notation, I don't know. What about this notation? It's fine. Anyway, the point is we can reduce everything to that, if we choose. Okay. So let's come back to the magic trick. So the magic trick is that, so we have tau, which is, where is it? Associative, we define an associative symmetric non-degenerate bilinear form. Okay. And we get two pairs of dual bases for this bilinear form. This one and this one are pair of dual bases because we exactly get that. It's straightforward to check. And this one and this one also are pair of dual bases. Also straightforward to check, completely trivial to check. So as I said, you have something completely trivial, but as a consequence, you will get something non-trivial, which is the first magic trick. Okay. So the existence, or let me write that before first. Exercise. In general, show that if T is an, if T is an associative, an associative symmetric non-degenerate bilinear form, then the sum for AI tensor BI is independent of the choice of the pair AI BI of dual basis for the bilinear form T. So be careful. What I noted, tau is what we did before. The bilinear form is like that. Here we just write T. Anyway, so in general, I guess to prove that I guess you need to assume finite dimensional. So if T is a symmetric non-degenerate bilinear form, so yeah. Anyway, so the exercise is to show that. So it should be finite dimensional. Should be finite dimensional. Otherwise, you may have some problem with the sum. So show that, or what? Or find a reference. It may be somewhere in the book. by Fulton and Harris. So the exercise is to prove that, or to find where it is written in Fulton and Harris book. Anyway, so this is independent of the choice of the pair of dual bases. But we have two pairs, so we can get an equality. Okay. So then, by the statement of above exercise, we have the relation 2, 3. We have two pair of dual bases. So you make one sum for one pair, this sum for the other pair, and you will get an equality because this is independent of the choice of the pair. This is magic trick. Magic trick. Okay. So sum for I in I, hi, xi, tensor hi star is equal to the sum for j in I and j fj tensor fj. Okay. Now we want to reduce that. We want to go to H. Here we are not in H. Here we are in H tensor H. We want to go to H. So we will apply some map. So apply identity tensor mu j for the character mu j corresponding to fj. So remember, character mean algebra morphism. So you get, so we apply identity tensor mu j. We apply that to this equality. So sum for I equal j xi hi xi tensor xi star equal identity tensor mu j sum for j in I n I f so nj sorry j tensor fj. Okay, so it's linear, so you can develop, and you get sum for I in I of hi xi mu j xi star. And let me put here an I everywhere, otherwise there will be confusion with the notation. I. And this is equal to, so here we use mu j fi equal delta ij. We recall that several times. Mu j fi equal delta ij. So it is equal to just ni f, so n what ng fg. So conclusion, fg is equal to 1 over ng sum for I in I hi mu j xi star xi. So we got under this magic trick, we got the formula for the primitive central idempotent fg for free under this trick. So and this involves, in fact, the entry of the character table, or if you want, the Fourier coefficient. Okay, and this is denoted equation 2, 4. Okay, and this, in fact, you can just write fj xi bar if you like. Yeah. Yeah, maybe. I don't know if I want to write that. Anyway. Equal to 1 over ng sum for I hi mu j xi bar and like that, if you prefer. Okay, so in fact, yeah, I did not. So we mentioned that in the introduction, you can put this out by replace it by the complex conjugate. And as I will explain soon, this is due to the fact this can be proved along the same line as we can do that for a fusion ring. In fact, you have as I will explain, you have the fusion coefficient make fusion matrices, and these fusion matrices are, in the abelian case, they are simultaneously diagonalizable. And the entry of the diagonal are exactly something like that. And so the point is that you have the fusion matrix of the dual is the adjoint of the dual fusion matrix, but adjoint map eigenvalue to complex conjugate eigenvalue, and so that's why you have that. But I will recall that. This was an exercise in the introduction, but I will, at least in the fusion ring case, I will explain. I will write the result. Anyway, so if you prefer, you can write on that anyway. Next, we will again apply something to that to get the first orthogonality relation. So that was used to prove, to get the formula for the primitive central idempotent. Now apply mu j tensor mu k we get mu j tensor mu k of sum. Oh, let me see. Maybe I can just copy and paste. No, not this one. If I'm not mistaken, copy, paste. Okay. And just have to modify it here. And okay. Mu j, mu k, mu j, mu k. Okay. So we have that. So this is equal to sum for I in I of hi mu j hi mu k hi star. And this is equal to, so again, we use the same thing as before. So mu j delta I equal delta I j. So what we get is so the sum I in I and I mu jfi mu kfi. So delta, I will just simplify, delta ij delta ik delta ij delta ik. So we can just replace. We only need j, and in fact, so we can take g ei equal j like that. So this is exactly what we get. And j delta gk. Okay. And so this is exactly the first orthogonality relation. Conclusion. We get the first orthogonality relation. Orthogonality relation. So the sum, so this one. No. Yeah. This one equal and j delta I delta j k. And that is the number 2.5. Okay. So that's good. Orthogonality relation, because if you consider that as, in fact, yeah, that as two, you can make two vectors. In fact, you can put square root of that, you can put it here, and you get two vectors, and you have on a usual complex vector space, inner product, you get orthogonality relation. Maybe you need to renormalize also. Anyway, I will mention something under this line for the second magic trick. Okay. Okay. So here I recall recall an exercise in introduction. So what I mentioned before, mu j xi star equal mu j xi complex conjugate. And so in the fusion ring settings, xi are the eigenvalue of commutative fusion. Commutative are the eigenvalue of the matrices of the matrix Nij k kg equal mi, but mi star equal mi star. So as usual, this is dual is adjoint, matrix adjoint, but whereas the eigenvalue of mi star are complex conjugate to of the eigenvalue of mi. That's why mu j xi star equal mu j xi complex conjugate. And something along this line should work for hypergroup. In fact, it should be exactly the same thing. Anyway, that's why we have this. Okay. Now, let's start from that and take G equal K. So G equal K here. So we will get 1 here. So we will get a formula for the formal codegree number. So take G equal K in and get a formula for the formal codegree, and here it's written G and G. So you get NG equal, so I equal J, G equal K, so sum for I in I, HI mu J XI mu J XI star, which is, okay, let me be smart. Which is, as I said, like that. which is sum of I in I, hi, complex modulus of mu j x I. And so this is strictly positive. So you have this formula for the formal category. Remember that for a commutative fusion ring, this is nothing but the square norm of the column of the character table. And it's strictly positive because this is strictly positive, and this is NII star 1 inverse. And this is strictly positive. So NII star 1 is strictly positive by the axiom of hypergroup. This is strictly positive, so it's strictly positive. So it's a result that the formal category are strictly positive. We already know they are non-negative, they are non-zero. Remember, we said tau of fi inverse ni. They are non-zero. But now we know they are strictly positive. Okay. So for a commutative fusion ring, it is just, as I already mentioned before, the square norm of the G's column of its character table. Fusion ring case. Okay. So now, second magic trick to get the second orthogonality relation. So, magic trick number 2 will be here. So the detail I will write is not written in the paper. It's just written. The paper is just written. It's a usual. It's a classical argument, and you do exactly as. So we get the second orthogonality relation in group theory. So I forgot to mention that the first and second orthogonality relation are not. This notion is known with this notation in group theory, in character theory of group. First and second orthogonality relation, as I said, corresponding to the orthogonality relation of the row and column of the character table up to the good normalization. So it's well known, and we can deduce the second from the first by this second magic trick. In fact, in my paper called interpolated, I don't remember, interpolated, I have a paper called interpolated something. I wrote this magic trick in details for commutative fusion ring. And so I added a reference to this interpolated paper. For this detail, I will write now. What color? This color. So let U be the matrix square root of hi divided by square root of mj mu j xi complex conjugate ij. So you consider this matrix. So this is a good normalization to get really orthonormality. Then the point 2, 5 mean that, so the first orthogonality relation, which is here. In fact, what I did here, I put the coefficient here, and I distributed here and here, and again for this one, by taking square root. And so I got something symmetric. And so, in fact, this relation means exactly that this matrix is an isometry. Mean that U star U equal identity, which means U is an isometry. And the trick is there, the magic trick is there, is that in the finite dimensional case, an isometry is unitary. And this is a magic. So I should put here. But in the finite dimensional case, an isometry an isometry is unitary. An isometry is unitary. And unitary is you have the other relation. Unitary means U star U equal U star equal identity. So you have the second relation for free because we are in a finite dimensional case. So U star equal identity also, which means that you have the second orthogonality relation. Sum or maybe let me continue a bit. Sum for J I. So you have, I hope I'm not making mistake like that. Mu J X I have complex conjugate. So the first and square root of H L N J mu J X L equal delta I L. I hope it's okay. Anyway. And so you can simplify. You simplify plus you take the complex conjugate and you get the second orthogonality relation which is that sum for J in I 1 over n J mu J X I mu J X L star equal delta I L H I inverse. Yeah, 2, 6. So, like that. So what did we do here? What did we do? So we group these two square root So maybe I have a coefficient problem somewhere. There is J. So you group together these two square roots, you get that. Then you can put that the other way. If I is different from L, then it's 0, so it's okay. So if it is equal to L, then you can group together. And you get that. And that's all. You get this second orthogonality relation by this magic trick. So one magic trick for each orthogonality relation. And no, now I will make the pause. So I just write the title. We will start a new subsection, and then I will make the pause. So two normalizable abelian hypergroup and their dual, and we make the pause. So what time is it? 6, 8, 2, what? 5 minutes. So like that. Oh, now it's like that. Okay. Pause. Okay. So let's restart. So we prove the two orthogonality relation. We have a formula for Fi, a formula for Nj. Good. Nj is positive. Okay. So now, new subsection, normalizable abelian hypergroups and their dual. So, normalizable, not that hypergroup can be rescaled as follows. Can be rescaled as follows. So let yi equal xi over alpha I for some non-zero complex number alpha I. Hypergroup, let me write it like that. H and the basis x, I, and I. So this is for the basis, B. Write the set. Can be rescaled as like that. So you have a new basis. We need the coefficient, we need the complex number alpha I to satisfy alpha 1 equal 1 and alpha I star equal the complex conjugate of alpha I. Let B prime B, yi, I, then HB prime is also a hypergroup. Let me write it like that. Tac. Wait. Okay. Anyway. Will be equal that. Anyway. I just wanted to make as clear as possible. Anyway. Okay, so okay, so you have this new basis, and why it is also a hypergroup. So let me briefly prove. Let me briefly prove this. So y1 is x1 over alpha 1, which is x1, because alpha 1 is equal to 1, is a unit. So that's okay. Yi, yj is x I alpha I times xj over alpha g, which is the sum k in I of 1 over alpha I alpha g n I g k xk, which is sum. So xk, to make it yk by putting a coefficient here. So it's alpha k over alpha I alpha j nij k y k. So the new coefficient are maybe cannot imaj k is alpha k over alpha I alpha j nij k. This is a new coefficient. But the problem is that I wanted to write nijk prime, but it's not very well. Nijk prime like that, not very good notation. Now, why it is? So why it is hypergroup? So M I star 1 is alpha 1 over alpha I star n I star 1, which is 1 over alpha I complex conjugate n. Wait. So n I star 1 So it's just like that. And I star 1 over the modulus, square modulus of x star, which is positive. So this is what we wanted to prove, the first axiom. Star, I star. And the second axiom is M ij1 is 1 over alpha I alpha j, and ij1, which is 0 if I different from j. So it's okay. Actions. Okay. So now now what about tau? What about, so we consider the new hypergroup now, renormalize like that. So alpha I, all non-zero. So what about tau, and what about the formal codegree? So tau prime of, so as it was defined before, tau is just that. The tau map of the renormalized, of the rescaled hypergroup. So tau prime of x I over alpha I is like that. So you have this by linearity. You just have alpha I delta I1. Now we will use that, and the formula we proved before for the primitive central idempotent Fj to prove that the formal codegree has invariant under rescaling. The formal codegree and J are invariant by rescaling. Proof, in fact, so recall how we define the formal codegree. Recall that Nj is, by definition, tau of Fj inverse. So let Nj prime to be tau prime of Fj inverse. So first observe that the primitive central idempotents do not care about the rescaling. In fact, this is just about the algebra. So you can define the new formal codegree like that. And we will prove, in fact, they are equal. And for so, we will just need to use the formula we prove for Fj by the formula 2 for tau prime of Fj is tau prime. So the formula 2 for is as follows. Sum for I in I of hi mu j xi star xi. So we develop by linearity, you get that hi mu j xi star tau prime of xi. But this is nothing. This is equal to alpha I delta I1, as we mentioned here. So you can just consider the coefficient I equal 1. So it's equal to 1 over nj h1 mu j of h1 star. So if you just write like that, alpha, no, not this one, alpha 1. Okay, so in fact, here you can simplify, you can just write alpha I. What? Oh, I see. So maybe it can be simplified even directly. You have that, but in fact, this is just delta I1. Because if alpha, because alpha 1 equal 1, and if I is different from 1, you have 0. So, in fact, you have something more direct here. Alpha 1 equal 1. So in fact, you have directly so tau prime equals tau directly. So there is no need to make any proof. Okay, so I can remove that. Oh, Oracle degree are invariant by rescaling. Anyway, so here you just have. So what should I write then? But this is not necessary. Okay, I will remove everything because it's useless. And right, like that. So tau prime equal tau. Conclusion. It follows that conclusion. The formal codegree are invariant by rescaling because remember how the formal codegree appears. Because NG equal tau of equal tau prime of fj. Anyway. So that's okay. So the point here is that we have that the difference appears only when it is 0. So that's why we have that. And as I said, the primitive central idempotent are invariant under rescaling. There's nothing, just a property of the algebra. So that's okay. Okay. So let me write note. Proof. Okay. Now, what about now? Okay. Okay. So the formal codegree are invariant by rescaling. Now, we'll consider a normalizable hypergroup. Recall the notion of a normalizable hypergroup from definition 1.5. And in fact, let me write it again. An hypergroup is normalizable if one obtains a normalized hypergroup after a rescaling. And we just define what is rescaling and just what normalized mean. Sum for I in I. Oh, what a... Sum for I in I and ij k equal 1 for all ij in I. So sum for k. Sorry. Sum for k. This is normalized. This is normalizable. Okay. Now we want to we will provide a complete characterization of a normalizable hypergroup. Before that, let me note this straightforward statement. Note that any rescaled normalizable hypergroup is also normalizable because the rescaling only involves non-zero coefficient. Alpha I is non-zero. So that any rescaled normalizable hypergroup is also normalizable. Okay, so the lemma characterizing the normalizable hypergroup is the following, and you will see it's quite interesting because it's related to character. In fact, an hypergroup is renormalizable if it admits a character which is non-zero everywhere on the basis. Or, if you prefer, if there exists, when you think in terms of character table of a group, if there is a column of the character table where every entry are non-zero. We know that for a group, it's always true. The first column is given by the degree of the character, so it's always non-zero. So the character ring of a group is always a normalizable hypergroup. So let H be, so this is the character relation, be a hypergroup. And you see the existence, we want non-zero column with non-zero entry. And you see it is related to the what we mentioned in the introduction about Burnside property. But Burnside property is about the existence of zero in some entry of some column or some row. Okay, so let HB be a hypergroup, then HB. So let me 3. So then HB is normalizable if and only if there is a character, an algebra morphism mu1 such that xi divided by alpha I, this rescaling is normalizable if and only if the sum for k in I of the rescaled coefficient, as I mentioned before, nijk equal 1, if and only if so you move that on the other way. No, what do you move? Yeah, you move that here. So you get alpha I, alpha j equals the sum for k in I of nijk alpha k. If and only if mu xi what so if and only if mu1 mapping x map to mapping, so mu1 of xi, mu1 defined like that, xi map to alpha I is a character, so an algebra morphism, because which means character mean what? mu1 of xi xj equal mu1 of xi, mu1 of xj. But this is clear because here it's mu1 of sum nijk xk, and here it is what? Alpha I, alpha j, and this is when you develop, you get sum nijk alpha k. So you get, you have this equality by, so this equality is equivalent to this, is this equality. So this is equivalent to this equality, which means that this is an algebra morphism. Okay. With, wait. So it's not enough. You also have, you also need, because alpha 1 equal 1, also you need that to get, we want your mu 1 of x1 equal 1. So you need also that. And also to get if only if, you need to come back here. And the assumption in the rescaling is that the alpha I are all non-zero. So if you want, it's not enough to have a character, we want also all the value to be non-zero. With, and you see, it's with mu I x, mu1 xi is different from 0 for all I. So you start from a character non-zero on every entry, you get, you call the value that non-zero, so you get this relation. This relation is equivalent to this relation, which is the definition of normalized. Is normalized. Normalized, sorry. Is normalized. Okay. And the other way, you just did that. You just did that. So it's okay. It's okay. So we proved this lemma. We proved that a hypergroup is normalizable if only if it admits a character which is non-zero everywhere on the basis. Okay. So now notation. The notation for a normalizable hypergroup. The normalizable hypergroup HB together with the character mu1 as in the previous lemma is denoted like a triple. Okay. You denote it like a triple. HB mu1. And when I write that, I mean a normalizable hypergroup with mu1 as in lemma 2.3. So I don't have to recall that. If I write that, writing that means that this is non-zero on everywhere on the basis. Okay. And the normalized hypergroup H normalized by mu1, xi divided by mu1 of xi I is denoted by HB mu1 overline bar like that. So it's normalized. Okay. Normalized is like that. Okay. So definition. Now we will consider the dual of the normalized hypergroup. Definition 2 for the dual. The recall from section 1.1 that any abelian normalized hypergroup admits a dual hypergroup H star. That any abelian normalized hypergroup H admits a dual hypergroup H star. So in the case of the normalized hypergroup of the normalizable hypergroup HB mu1, we denote this dual by like that. HB mu1 hat. So we don't write, we may write HB mu1 like that, but in fact, we just write like that. Okay. Okay. Okay, now what about the coefficient on the dual? Let HB mu1 be an abelian normalizable hypergroup. Be an A on the dual. It is equation 1.2. It follows. So remember that this was done for abelian normalized hypergroup. So, so you can get a more general form. Now we can get a formula not for abelian normalized hypergroup, but for abelian normalizable hypergroup. It follows that the multiplication on the dual HB mu1 hat can be written as follow. So you just copy and paste the formula for the abelian normalized case we did in the introduction, but you replace by the basis. You take the norm. We want the normalized basis. So it applies on the normalized basis. So you apply the same formula, but you put here the normalized basis. F of xi over mu1 xi times g xi divided by mu1 xi. Okay. For all fg in the dual. Okay. And, so trivial. So that's all. So next time we will start by mentioning and proving very, very easily that the mu1, which is in x star, is the unit of that. So remember, the algebra here is x star containing mu1, and this mu1 is a unit of this algebra for this multiplication. And in fact, it's completely obvious. You put mu1 here, so you get 1, etc. Okay, so see you next week.